Good afternoon everyone. Myself Gunjan Kumar will present an overview of our work, Personalized Recommendations for Modes of Transport, a sequence-based approach. My co-authors are Dr. Hussain Jerby and Dr. Michael O'Mahony. We are from Insight Centre for Data Analytics at University College Dublin, Ireland. Nowadays, we are surrounded by different kinds of sensors in our day-to-day lives, whether it be at home or outdoors. For example, there are sensors in our phones and data is collected through many of the apps we use. Some of my colleagues even wear wearable cameras, and we have more and more wearable devices coming out every day. These sensors result in collection of rich user activity data. Such data is sequential. Users perform activities in sequence, in patterns, sometimes consciously, at other times without conscious thought. And these activities have associated context such as location, time, weather, etc. The past activities we perform along with their context can influence our next activities and when, where, with whom we perform them. For recommender systems, such rich user data facilitates real-time recommendations for a given user and context. In our previous work, we proposed a generic recommendation framework for sequence and context-based activity recommendation. In current work, we address the problem of recommending the next mode of transport to users. But why recommend mode of transport? A motivating application domain is mobile personal assistants such as Google Now and Microsoft Cortana. These applications seek to show users the right information at the right time. For example, at the end of our usual working hours, these applications proactively show us the estimated time to home. However, when using these apps, users need to pre-select a particular mode of transport. We believe it will be more useful if instead suitable modes of transport are recommended to users. Furthermore, recommending mode of transport will also help us better plan our days, facilitate travel, and help service providers better cater to the needs of the community. When we look at related work in urban computing and recommender systems domain, we find interesting works which capture sequence and user activities. For example, hierarchical graph-based models and old Kth-order Markov models. However, these approaches do not leverage the context of user activities. Popular approaches for capturing context are tensor and matrix factorization models, but these do not capture the sequence information. While capturing both sequence and context has been suggested to improve recommendations, there are very few such works. In a previous paper, we proposed a content-based activity recommendation framework which leverages both sequence and context. Recently, a stochastic modeling approach has also been proposed. Our main contributions are a content-based approach for recommending the next activity, mode of transport, based on past activity patterns of users, extending our previous work with new approaches to extract and match subsequences drawn from past activity patterns, a machine learning approach to learn the optimal subsequence length for matching current and past subsequences, and experiments on a real-world mode of transport dataset. Now I'll present the recommendation framework and subsequence matching approach. Here is an overview of our framework. The key processes are data modeling, timeline matching, similarity assessment, and ranking. First, the data is to be modeled as timelines. A single occurrence of an activity is considered as an activity object. The activity object consists of a set of features like the mode of transport taken, start time, duration, distance traveled, etc. When we arrange activity objects chronologically, we obtain activity timelines. Here we show three activity objects in a timeline representing a commute. These timelines will now be fed into our recommendation framework for matching. Consider the user timeline shown. Here each colored block represents an activity object, the color representing the name of the activity. We identify the current activity the user is performing. Our task is to recommend the next activity for the user to perform. How do we do this? We look back into the previous occurrences of the current activity for that user. We extract subsequences from the user timelines where the last activity corresponds to the current activity, the current timeline for the most recent current activity, and candidate timelines for previous occurrences. The challenge here is, what should be the length of the subsequence? This is the matching unit. In this paper, we propose an n-count matching approach, where the preceding n activity objects are included in the subsequence, shown here for example n equals 4. Next, similarities are computed between current timeline and each candidate timeline. For this, we use a two-level edit distance measure, proposed in our previous work, which considers both sequence and context. Ranking. Every candidate timeline is going to suggest one activity object, that is, the one which takes place after the current activity. Now, the task is to rank the activities recommended from each timeline. For this, scores are assigned based on how similar the candidate timelines were with the current timeline. Finally, a ranked list of recommended activities are produced. But wait, what about the value of n in n-count matching? Here we look at how recommendation performance varies across different values of n. Here we show 3 different representative users, and higher MRR on the y-axis means better recommendation. We find for some users, like the user in blue, very low N is best, while for other users the best N for recommendation is slightly higher, for others more higher, like the user in green. This suggests that choosing the right matching unit for each user is important. For this, we propose a machine learning approach to learn optimal N for each user, recognizing that each user has different regularity and repetition in their activities. A supervised classification approach is proposed. However, given the natural variation in activity patterns of users, learning an exact value of N is not feasible. Hence, the approach is to learn a range of values within which N is likely to lie. The table here shows the 3 ranges for N used in our experiments. For classification, each user is to be represented by an attribute vector. Before attributes are extracted, timelines are decomposed into feature sequences. A user timeline is a sequence of activity objects, where each activity object consists of a set of associated features, say for example start time, distance traveled, start geocoordinates. So a timeline can be decomposed into corresponding feature sequences, one for each of the feature. From these feature sequences, we extract attributes to characterize each user. Our attributes belong to 2 categories, those capturing regularity and those capturing repetition. For capturing regularity, we use sample entropy based attributes. Sample entropy has been used to quantify regularity in physiological and biological time series. In essence, it is the conditional probability that 2 sequences which are similar for p points remain similar at p plus 1 points. We extract sample entropy for each feature sequence and mean and standard deviation of sample entropies over all feature sequences. For capturing repetition, we use k-gram based attributes, namely the number of distinct k-grams, the mean and standard deviation of frequency of occurrence. Based on these, we extract a number of attributes to characterize each user's timeline. Now an overview of the experiments performed. We use the GeoLife GPS trajectory dataset and extract a subset which contains labels for modes of transport. The timelines constructed have 51 days, 334 activity objects and 18 users. It contains 9 different modes of transport such as bike, bus, car, etc. and 7 features such as start time, distance traveled, average altitude, start and end geocoordinates, etc. Each user's timeline is split into training and test timelines, with most recent 20% days in the test. Our evaluation measure is mean reciprocal rank, which considers the rank position of the target mode of transport in the recommended list. We have 4 recommendation algorithms: our proposed N-count recommender, day-wise recommender from our previous work, and high occurrence and high duration recommenders as baselines. This box plot shows the distribution of recommendation performance as mean reciprocal rank over all users for different recommendation algorithms. We find that our N-count approach outperforms other approaches. For learning the optimal matching unit, we perform attribute selection using a wrapper approach and then use C4.5 induction to predict the optimal matching unit ranges. We obtained good classification performance with weighted average precision and recall about 0.78. More importantly, when the predicted N is used for recommendation, the mean reduction in MRR is only 3.1%. That is, using the predicted N is nearly as good as using the actual best N. In conclusion, experiments on a real-world dataset showed good results for our proposed content-based recommendation approach, which captures both sequence and context, our N-count matching approach, and our approach for learning the optimal matching unit. We recognize there is rich scope for future work, for example, to consider socio-economic characteristics and travel variables, recommending sequences of activities and context, which looks very promising to us, and to address the scalability and sparsity issues. Thank you, and I'll be delighted to answer any questions through email.